Most people think digital twins are just advanced simulations, but the truth is far more practical. A digital twin is a continuously updated virtual copy of a real physical system. Long before the term existed, engineers already compared real performance with theoretical models. Digital twins simply close that loop in real time. To see this clearly, imagine a simple everyday situation where you track your fitness using a smartwatch. It measures your heart rate, steps, and sleep, compares them to expected values, and alerts you when something is off. Without realizing it, you're interacting with a personal digital twin, a live model of your body's performance. What's actually happening here is simple. Sensor data from a real system continuously updates a digital model, allowing engineers to compare expected behavior with actual behavior. When the two start to diverge, it signals wear, inefficiency, or an upcoming fault. Unlike static simulations, digital twins evolve as the system ages and conditions change. Now imagine a real mechanical system, an industrial gas turbine running 24/7 in a power plant. Engineers build a digital twin of the turbine using CAD, FEA, CFD, and control models. Sensors on the real turbine stream temperature, vibration, pressure, and load data into the twin in real time. As conditions change, the digital twin predicts how efficiency will drop, where thermal stress will increase, and when components may fail. Engineers can test operating adjustments virtually before applying them to the real turbine. Nothing is guessed. Decisions are validated digitally before touching the machine. This same logic is already used across industries. Aircraft engines are monitored using digital twins. Wind turbines optimize performance based on weather. Manufacturing lines adjust parameters in real time, and HVAC systems adapt to occupancy and climate. Digital twins turn maintenance, optimization, and control from reactive tasks into predictive ones. The concept of digital twins in engineering was formalized by Michael Greaves, who described how physical systems and virtual models could remain permanently linked through data. This idea transformed simulation from a design stage tool into a full lifecycle companion. In practice, a digital twin follows a clear workflow: physical system, sensors and data, real-time model update, simulation and prediction, engineer decision, system adjustment. The engineer stays in control. The digital twin provides foresight, not authority. Now that you understand the intuition behind digital twins and real-time performance prediction, the next natural step is to explore smart manufacturing and Industry 4.0, where entire factories operate as interconnected digital physical systems. And that's exactly what we'll break down in the next episode.